All right, welcome back. So, obviously, sedimentary rocks can be stratified, but so can other types of rocks. Not always, but so can other types of rocks. You know what? Before we get into it too far, let me go ahead and give you the first part of the super secret code. It is the number 6. You got me? The number 6. One more time. The number 6. All right. So lava flows and intrusions, igneous rocks, sometimes can be stratified. So if we can determine the relative age of lava flows, which, once they flow out onto the surface, could be horizontal strata, sills, which move horizontally through layers of the earth, and associated sedimentary rock, we can use contact metamorphism and inclusions to kind of figure out, well, where do these igneous rocks play a part, relative age speaking, as compared to these other sedimentary layers, sedimentary strata, and these other rocks that we see. I touched on the idea of contact metamorphism a little bit in the kind of helper video in the Unit 4 lab. Make sure you're watching those videos, right? Make sure you're watching all of those videos. So how can you determine, for example, a layer of, let's say, basalt, which is an igneous rock? It is a very flowy, runny type of lava that if it flows out onto the surface, it's an extrusive igneous rock. It's volcanic, so it erupts and flows out very gently, kind of lava flows we would see in Hawaii. So as it flows out, it can create that layer of material, and through time you can get other things built on it. But anyway, how can you determine whether a layer of basalt within a sequence of sedimentary rocks is a buried lava flow, which is an extrusive event, or a sill, which is a magmatic intrusive event? Let's say that basaltic magma starting to make its way up through the layers of the earth. It doesn't erupt, but kind of goes sideways horizontally through the layers of the earth, and that's a magmatic sill. Touched on those type of igneous bodies in Unit 2 lecture. Okay, but anyway, how can you tell? So what we have here is visually a basaltic lava flow. In fact, there's a number of them that have occurred in this particular area. You can see the different layers of different flows, just as an example. But in any case, a lava flow forms in sequence with sedimentary layers. So it might have a sandstone, a limestone, lava flow, shale, sandstone. So these are the different events that have occurred over time. So the way you can figure out it's a lava flow, though, is that rocks below the lava will have signs of heating, contact metamorphism, but not the rocks above, right? You get some rocks and you get this hot lava flowing out, and it begins to cool to form that rock layer. Well, it's going to apply heat and start to bake the rocks below it a little bit. So we have some contact metamorphism via heat in this case. It's going to alter kind of this top part of the layers of rocks below it. Then over time you might get more sediment deposited on top, which eventually forms rock layers. But this is forming now on top of cooled lava. This is turned to rock already. So when you're looking at the bottom of those, say, sedimentary rocks, you're not going to see any contact metamorphism or any baking. The rocks above, though, may have inclusions from the lava flow below. Remember, the pieces of the rocks are older than the rocks that contain them. So here's an example. So this is how you can tell. If you're looking at layers, you have 1, 2, 3, 4, 5, 6 layers. This is how you can figure out this was a lava flow initially and not just an intrusion of magma cutting through between 2 and 4. That's because you'll see this baked zone, this zone of contact metamorphism. This rocks below were just kind of baked a little bit, right? Just baked a little bit, but what you see above, you don't see that contact metamorphism, but you can see pieces of the lava flow embedded in the sedimentary layer above. The rock is older. This piece, part of the lava flow, is older than the surrounding rock. So that's how you can tell this is a flow. There was only contact metamorphism on one side, and then these layers were later deposited on top. That's a little bit different than when we're looking at horizontal sills. A sill will heat the rocks above and below. An igneous sill is when magma kind of just cuts through horizontally in either direction into the rock layers, usually a bedding plane or some transition from one rock to the next, some easily accessible crack that it will get into and move horizontally. So what you'll see in that case then is a little bit of contact metamorphism above and below. In reality, you're looking for kind of a change in color is sometimes a good indication of contact metamorphism. But the sill itself might also have rocks from either above or below embedded into it. So let's take a look at this one. This is actually a very famous one. We might have to look at this one in lab a little bit. But this darker rock is kind of a basaltic magma intrusion, it looks like, cutting through. And you can see above and below these rocks are different, but right at the edge here, all right, right at the edge here. So this is a different rock layer, but right where it's in contact with the igneous intrusion, you can see it changed color a little bit. It got baked. Same thing down here. It's kind of grayish rock right along here where that hot magma cut through, kind of baked and altered that a little bit. And that color change is kind of an indication of it. So in diagram, if you're looking, it's almost a very similar diagram to the 2 slides ago, but now you can tell it's a sill, not a lava flow, because above and below you have that contact metamorphism on both sides. Additionally, you have the pieces of rock that are embedded in it. So these rocks, remember, the pieces are older than the intrusion, so this intrusion came at a later time. A little review again on unconformities. Remember, these are gaps in time, gaps in the geologic record. It could be an indication of crustal deformation, weathering and erosion, sea level variations. And we talked about 3 different types: disconformities, nonconformities, and angular unconformities. More information on that, make sure you're going back and checking out the previous unit, lecture, and lab material. And with unconformities, the rock record is incomplete at these locations. In the previous unit lecture, we looked at a diagram of how angular unconformities are created. Let's look at a diagram now of how, let's say, disconformity is created. All right. So let's say, so this is million years ago. All right, so that's 0 million years ago, the present, all the way back to 12 million years ago. So 12 million years ago, we start to get rocks being deposited. Typically, when you see, kind of like when we looked in the lab, you see the sedimentary layers with these lines that indicate some side of mudstone or shale. The ones with little sandy-looking things, that's sandstone. The ones with blocks are limestone, but all sedimentary rocks. So you get sediment deposition and lithification, starting 12 million years ago, blah, 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 blah. So then we get to about 4 million years ago. And then for about 1 million years, from 4 to 3 million years ago, weathering and erosion kind of just ground down what was there. So for the next 3 million years, weathering and erosion ground down what was there. So now we're left with this. Now, starting again about 3 million years ago, sediment started being deposited again. This looks like maybe a conglomerate or some sort. I forget what that symbolized. But again, you get sediment being deposited and lithified, turning to sedimentary rock, starting about 3 million years ago to just about the present. So, but that's going to form right on top here, right? All of this was weathered and eroded, so that's going to form right on top. So what we would be looking now at the geologic record, if we were standing here looking at the side of the cliff and seeing all these rocks, we would see these rocks. These are 12 million years old, and all of a sudden we get this rock, which is about 6 million years old, and this rock, which is 3 million years old. So we have some missing information in between 2 sedimentary layers. That is what's known as a disconformity. All right, so that's kind of what we see. I'm gonna move me a little bit. So you can actually get a number of different types of unconformities, kind of next to each other, especially if the unconformity happened kind of over a large regional area. So unconformities of regional extent may change from one type to another along kind of that unconformity. And there also might be varying amounts of material gone, so they may not represent the same amount of geologic time everywhere. But this is all one kind of unconformity, but if I look here, this is a disconformity. Sedimentary layer, sedimentary layer. If I look at this point, it's an angular unconformity because I have horizontal sedimentary layers and angled tilted sedimentary layers. Over here, I have a nonconformity, sedimentary layers and then igneous rock below, plutonic igneous rock below. So it's still all the same unconformity, but just depending on where we look at it, it kind of changes the type, especially if these are large regional events, large-scale weathering and erosion or deformation. What else we got here? I'm going to move me. Oh, terminations. I don't know why the Terminator just popped in my head. So layers of sediment, this is the principle of lateral continuity, extend outwards in all directions until they terminate, until they end. Terminations may be kind of abrupt. They may just end at the end of some sort of basin, say sediments being deposited in this wide canyon or whatever it is, and all of a sudden the sediment just terminates, it stops because that's the edge of the canyon that the sediment is contained in. Or they could be kind of truncated, stopped by faults, like all of a sudden, this stops right here, all of a sudden this stops right here. So, where they terminate, they can be, again, abrupt. All right, they can be abrupt, where these terminations, where the sediment ends, or they can be gradual. There's some weird animations going on here. Or they can be gradual, where a rock unit becomes progressively thinner or kind of just pinches out. Maybe it wasn't bounded by some sort of basin, or maybe there wasn't a fault. It's just the sediment just kind of thinned itself out. So like in an example here, the sediment that created this type of rock is just kind of thinning itself out. It could also split into even thinner units, and that's called intertonguing. Or you can get a gradual termination where one rock unit changes by lateral gradation. It's subtly changing sideways, laterally, as its composition or texture becomes increasingly different. So it can be kind of thinned out until it's gone, or it can just gradually, subtly change as it continues to happen. That's a lateral gradation. So either it thins out, or it just kind of the same stuff, but like look at in between these dashed lines. It just kind of subtly changes as you go across there. So that's lateral gradation. Now with these two things, this is what we see occurring due to sea level rise and falling, changes in marine and coastal environments, which will be the next section. One last term, and then we'll pause here, is called Sedimentary Facies. I didn't come up with the word. Sedimentary Facies. So both intertonguing, what we saw, that kind of thinning out, or lateral gradation, indicate simultaneous deposition is occurring in adjacent environments. So we're not talking about vertically now, we're talking about horizontally. Something's happened a little bit different here, and somehow they're kind of changing sideways. Not changing vertically, but changing sideways. And what a sedimentary facie is a body of sediment. It has distinctive physical, chemical, and biological fossil attributes, and they're deposited side by side with other sediments and in different environments. They indicate different rocks, mostly different environments, but something different going on sideways. We're not looking vertically now. Now we can also look horizontally. And this is kind of what we see. Again, maybe a limestone facie, intertonguing with shale, intertonguing with sandstone. Kind of pretty much the same thing here. And a lot of this happens when we're talking about marine and coastal environments and sediment deposition therein, which again, not all, but most sedimentary rocks indicate that sediment was deposited in the shallows of the ocean. Grand Canyon is a great example of that. So you can get, again, limestone, shales, sandstones, and even integrating with other things like coal. So you can start to see it changes in environments horizontally. So anyway, let's pause there. When we come back, let's talk about coastal and marine environments and how all this plays a part. See you back here in just a second.